Okay guys, so let's keep going, and now let's talk about a different technique which is called the red pill. The red pill is actually a really old technique which is used as an anti-VM or VM technique in order to know if it is running under a virtual machine. But as I said, it is really old, but still I'm gonna show you so that you can see other variants. So in order to do that, I'm going back here to the main functions, and here in the red pill you can see, let me double click on it. Basically the way it works is that every CPU, okay, every CPU has something that is called an interrupt descriptor table. Okay, that descriptor table, it is unique per CPU, but when you are using a virtual machine, that descriptor inside the virtual machine must be different, because it cannot be the same as the one being used in the host machine. That is, and because of that, you can use the SIDT instruction, which is basically saying, give me the value of the interrupt description table, and that's the reason of IDT. And it is well known that VMware will have an FF in that value, and therefore you can see here that it is gonna execute the instruction. Then here it's gonna copy the result into EDI, and that result is gonna move to EAX, and then it's gonna copy with FF. In other words, if FF is present in the result of that specific value, and therefore it knows that it is running inside a virtual machine. In other words, it's gonna say here, hey, if you are not equal, then here, no VM present. Okay, and obviously here, semicolon, VM present. Right? So as you know, if it's the same strategy, it's gonna take two branches with different values. Don't care about that. The only thing that we care is to bypass this check. Okay, but since this is an old technique, the red pill actually doesn't work with the latest virtual machines, because they have other values. Probably there is another reason, but during my test I realized that actually the value is not even FF, and therefore I don't need to patch anything. Okay, so let's test it. Again, we go to the return here, press F2, then play button to get to the end of the function, press F7, and now we are here in the next instruction, which is red pill. We go there, and we are about to execute the SIDT. And something that I forgot to mention, there is a register called IDTR. That register is the one which is gonna be storing the value of the interrupt descriptor table, okay, in memory, and therefore that's the value that is gonna be saved after executing the SIDT. So we execute it, we put the value in EDI. Let's click here, and you can see that EDI doesn't have any FF, and we are running inside a virtual machine, right? It should have an FF there. That's the reason I'm telling you it's not like something that reliable to test nowadays. It was something effective years ago, but not today. So as I said before, it is gonna move the value to EAX, and then an AND in EAX to just keep the most significant byte, which is 80 in this case, and then it's going to be compared with FF. As you know, it's not equal, which the jump is taken, right? We don't need to do anything. We jump into this branch, not being present. So, and that's just because that specific instruction is not reliable. So I just wanted to show you what is the red pill, so that in case you see it in the code, in malware, you know what you are talking about, but even though it's not a reliable option. Okay guys, let's keep going, and now we're gonna talk about another technique in order to detect if the malware is running inside VMware. It is a specific technique to detect if it is running inside VMware. Okay, the way it works is here. By the way, you can find this technique if you ever see this combination of hexadecimal values, which actually means VMXH. That's a magic number. Okay, so that magic number basically is going to be used to query the port in VMware. Okay, and once the port, which actually is this 5658, if you query that port, okay, with this instruction, with this command, sorry, 0A, which is stored in ECX, when you query that instruction via IN, if you're running inside a virtual machine, in this case only inside VMware, that magic number is going to be stored in EVX, okay, which is being saved here in the result. And then you can see here that it's going to be comparing that if the result of that value was the magic number, and if that's the case, then VMware found. Okay, as we know, if we run it, we should go and take the jump. Okay, so let's test it to see how that works. Again, we are here, we go to the end of this function, which is not the one we're using, play F7, F7, and we are here. Okay, so eventually, let me go to the meet. Here is the magic number being copied to EAX, then the command to be executed, the port, and here is the instruction, and check EVX. Okay, we press F7 and see EVX is holding the magic number as expected, which means that when we come here and do the compare, we know that both are the same, and therefore the jump is taken. Okay, so obviously, and as usual, we can do many different things in order to bypass this check. We can always come here and change the logic of the jump, as we saw before, you know, if you want, or you can change the value here since it is hard coded. You can change this value to another, let's say 7, right, so that it will always be different, and therefore we can bypass the check. Okay guys, so this is just another technique in order to detect virtual machine through the ports query. Okay guys, so let's talk about the next exercise, which is output debug string. That's a technique to check if a debugger is present. As you are seeing, I'm I'm showing you techniques to check if it is a virtual machine or if it is a debugger present. So those are different checks: anti-VM, anti-reversing, or anti-debugging. Okay, so this is an anti-debugging technique. So we click on it. It's pretty simple. So it's gonna set an error in the system, 1 2 3 4, and then it's gonna print a string in the debugger. So this API works if there is a debugger. Actually, it is just to print something in the debugger console. But if there is no debugger, okay, it's gonna generate an error, which is gonna be caught here, and therefore it's gonna check, hey, the last error is equal to 1 2 3 4. If that's the case, if it is equal to 1 2 3 4, sorry, first of all, if it is not equal, it goes here, which means there is no debugger. In other words, there was an error generated when you call output debug string. But if you are equal to 1 2 3 4, that means there was not error because the debugger was present when I call output debug string, and therefore the debugger was found. Okay, so if we run it right now, we should go to this branch, which eventually will put in EAX 2492. Let's check it. So we put F8, the push 1 2 3 4, the error is set, then it's gonna push 2 question marks. That's just for some encoding, don't worry about that. And when we call output debug string, check the window. It just prints those 2 question marks as expected. No error, everything is fine. So when it gets the last error, it comes here and say, hey, is the last error equal to 1 2 3 4? You say yes, it's the same because there was no error generated, and therefore we jump to the move EAX 2492 instruction, which, as you remember, that's the instruction that detects the debugger. Again, if you just want to bypass it quickly, you just change the jump not equal to jump equal, and therefore you're gonna jump to the other branch. Okay, that's it about it. Okay guys, so let's talk about our last technique in these different examples about anti-debugging, anti-reversing, and anti-virtual machine, so which is called anti-global flag. The anti-global flag is actually a value inside the process environment block, which basically are flags set in the heap when you are debugging a process. In other words, if you are using a debugger, there are gonna be some flags set, and that value of those flags is gonna be checked, and if it is present, the malware knows that there is a debugger. But if it is not present, then the malware knows that there is no debugger found. Okay, so it is just same strategy as we are seeing before. So we go here. The only thing different here, guys, is that, again, as you remember, it's gonna be accessing the PEB with FS30 in EAX, but in this case it's gonna jump 68 positions ahead, and it's gonna compare it with 70. Okay guys, so guess what you need to know? You need to know how to patch this specific value if you wanna do it in the fancy way via the Python API, and you just change the value, right? It is calling 70. If it is different than 70, in this case it says, are you equal to 70? If it is equal, the flag is not clear because it is jumped over. Let me just put here an N and put flag here. Okay, so if it is equal, the flag is not clear with 0, and then when it is compared here, it says no, not equal. That means debugger found, right here. But if it is equal to 0, no debugger found in the left side. Okay, so we want to go to this branch, right? Let me show you how we can see that offset by using WinDBG. Okay, again, we have WinDBG here, and with WinDBG we can print a lot of different cool stuff. As you remember, here we just enter the Bang PEB, which means all the content of PEB, right? But there are other ways that we can print the content. For example, we can do DT, okay, NT, which is where the process environment block is located inside NTDLL, bang underscore PEB, enter. And this instruction is gonna give us all the offsets of the PEB. We can see here, if you remember, that offset 3, but 3 because keep in mind it starts at 0, right? 0, 1, 2. So on offset 3 we have the being debugged. You remember that? But now if you go to the code, it is saying offset 68. Let's go to the offset 68. Here it is. This way we know what that offset 68 is talking to. Now we know that it is anti-global flag. You can Google it and you will start understanding what that flag is doing. Okay guys, because I'm teaching you, but what if tomorrow you get an PEB plus 28, for example, or plus 80? So you will always know how you can get the values. Okay, so now that we know that it is anti-global flag, we can get more information about it. You Google it, you will see that it is related to the heap. Debug flags being used when you are debugging. So the heap is set up in a proper way. So we say here heap -s, then NT global flag, enter. And here basically what it's gonna say is what are the flags enabled. You can see that it is tail, free checking, and validate parameters. Those three flags, if you add them, the values of them, is gonna give you the number 70. That's the reason that we see here that it is comparing with the number 70. Okay, another way for you to validate this is you just put the bang G flag, and it's gonna tell you the similar content. As you can see here is 70 based on these different flags. Okay guys, so basically anti-global flag, it is gonna be set some flags when the process is being debugged, and therefore the heap is gonna be set up in a different way with those specific flags. Okay, and therefore this is also a way for the malware authors to check if there is a debugger present. So summarizing guys, you realize that there are multiple ways to ask the process itself or the environment in order to know if it is running through a debugger or if it is running inside a virtual machine, and if you open it in IDA, it's gonna be able to break the code so that it is more difficult for you to analyze it. Okay, so always try to understand what the code is doing and then check in internet, like in this case, process environment block, check the offsets and understand what's the purpose of that specific value, and then see what is the reason the malware is using it.